supportive ventilation. So it does reduce infiltration, and that's really critical for energy performance. It also allows you to control those input pathways. And without controlling those, you don't have any filtering or tempering on the air. So you really are just bringing in ambient conditions. Get to improve the indoor air quality, and they do work in dry or warm climates. So that's their application space. On the other hand, as we said, they do have an increased energy consumption. There's no heat recovery. Not so effective in humid climates, as we can see often in colder parts of the country. And the pressurization and interstitial moisture conversation. These are quite sensitive conversations. The pressurization one can be addressed, especially with the newer builds with passive ventilation, trickle ventilators, background ventilators, depending on where you are in the world. The interstitial moisture, that one, if you provide the correct air pathways and your home has enough places that you can actually push air out of, the interstitial moisture problem prescribed isn't such an issue. Negative pressure, and I put these two together. We are seeing a lot more of negative pressure coming in at the moment, particularly with continuous mechanical extract ventilation. And the mechanical extract ventilation, so you'll see throughout the slide I use MEV or CMEV for continuous. It's got some really key benefits as well. So they've got the more efficient removal of pollutants where positive pressure doesn't. So you get to actually target those pollutants at source. You've got the cost savings if you've got intermittent. So rather than the continuous, you've got less running time, although they tend to use less efficient fans because they're cheaper to run by running less often. Then you've got the demand control potential through typical continuous solutions. So the continuous solutions, because they're running all the time, are able to put sensors in their airstream or even in the space to respond to what's happening, and that can improve the efficiency. And they work well in colder climates. On the other hand, there is increased infiltration, so that's that uncontrolled filtering or tempering of the air coming in. There's also, so from that, you've got the uncontrolled heat loss. You don't know what you're bringing in. And there's some concerns in warm, humid climates. You get the opposite issue as well with depressurization over pressurization. So again, you need those prescribed pathways in more airtight homes. And in humid, hot environments where you're cooling inside, you could have the same discussion on interstitial moisture as you do for PIV. So two sides of the of a coin there, two options. In New Zealand, we're seeing a lot more continuous mechanical extract coming in, and that can be credited to Homestar. From there we get balanced, and balanced is an interesting solution. Balanced is typically a combination of continuous mechanical extract or PIV. There are two clear pathways where you control the air in both directions, and you need that well balanced, like actual commissioning to balance the solution. Why would you use it? You've dealt with the uncontrolled infiltration sources by putting a prescribed controlled pathway in. They're valuable in more airtight solutions and situations. So basically, if you have built those houses that we're thinking we're building right now, if not for the last 5 years, you know where the air's going. The pressurization issue that we discussed earlier, you avoid doors slamming or flying open. And there's actually some interesting health and comfort concerns from pressurization. A little bit of a black hole if you want to get into the detail. But when you have a low pressure space, it can actually cause joint pain because what happens is the air inside our body starts to swell up in those spaces. Not an expert on it, but really interesting kind of rabbit hole if you ever want to go down it. And as I said, how PIV plus CMEV. What we actually prefer when we're looking at balanced solutions, though, is MVHR. So MVHR, really simple. You guys know most of this. It's more energy efficient. Intrinsically balanced. I say intrinsically balanced. Again, attention to commissioning and installation is really important here. You do often get more advanced controls, and they work well in extreme climates with a higher temperature differential. On the other hand, they do cost more, they're harder to install, they take up more room, and really the effectiveness is debatable in older houses. Now, I'm not saying they don't work. Let's be clear on that. They do work, and they work fantastically. But if you haven't got an energy efficient home in the first place, your benefits will be less because you're not seeing those same savings. And in milder climates where the temperature differential is lower, they don't have as much effect as well. Now, under MVHR, there's a few things we can talk about. One is heat recovery versus energy recovery and where they're most beneficial. I spent a little bit of time working through this, particularly on the climate section. So you guys should hopefully all know sensible versus latent recovery, so whether or not you're actually getting the humidity and the moisture passing through the core. So the heat recovery is suitable in wet room extract, and we're seeing a lot more of that in New Zealand while we try and reduce costs and remove our intermittent extract and replace it with a whole house solution. Whereas with the energy recovery, they might typically have more of energy efficient performance, but they can't do those wet rooms. So you still need an alternative solution for those contaminated spaces. When we're talking climates, moderate/marine climates, they both work quite well, and that's where New Zealand mostly sits. Pretty much our entire country, either or does work, so we need to get into more detail if we actually want to look at which is the better solution. In saying that, if you're in a hot and dry situation, heat recovery does tend to be better, and that's because you don't need to worry so much about equalizing that humidity inside. On the other hand, in cold and dry situations, if you're bringing in too much cold, dry air with a heat recovery solution, then you can actually end up causing a home to be under-humidified, so under that 40% humidity target. Now, not such a big problem in New Zealand. We tend to have more humid climates, but we do see it a little bit in the lower South Island. And then the last one is they work quite well in hot and humid climates as well, and that's because they exchange some of that moisture coming in from the leaving air that's drier, assuming it is drier. The MVHR, where does that leave us? That's your solution suite of different systems that we're looking at. As I said, POV and MEV together make a balanced system, and then you work through natural balanced MVHR as well. Which brings me to the New Zealand factor. Now, this one's interesting. Brands has done a lot of research on different types of homes, and Renovate is one of their resources. So I've pulled this from their website and summarized it. And I had a look at the different homes that they had on there, which were villas, bungalows, Art Deco, and then they looked at 40s to 60s and 70s. And really, one of the key things that we talk about is that those older homes are drafty. And some of that comes back to how they're constructed. So a lot more timber was used. They didn't have hard wall linings such as plasterboard. And they also didn't use underlays. They didn't have insulation. They had an open fireplace. I know a lot of those homes now have those fireplaces closed up, but there are still some out there that have them open. It changed a little bit as you came into the 30s, and we started to see homes that didn't have as much cavity space. So the cladding was fixed straight onto the timber, and then the lining was on the inside. And those homes have seen a lot more weather tightness issues, often actually from the roof pitch or the roofing material and the lack of exterior guttering. They still had the open fire, so most of their issues were from weather tightness, not necessarily humidity inside the home, because they did still have drafts, especially through the windows and doors. 40s to 60s, we are seeing a change. It's getting less drafty. Open fires were less common, and they started to have underlay on some of those homes, but insulation was still rare. Now, something I learned quite recently was actually for the 70s that we didn't require insulation in any homes until 1978. A few local councils started introducing it in the early 70s, but it was 1978 when it became part of code. And these homes were getting more airtight, underlay was a lot more common, and you weren't seeing open fires as much either. On the other hand, the construction, a lot more mixed, harder to make some assumptions about what's going on there. Which brings me to the brands results. So if you haven't seen this before, you can see the link at the bottom, and we'll make sure these are available to you after the presentation. But you can see the trends from the 60s all the way through to 2010 plus, and that's the absolutely massive spread. So it's a box and whisker graph there, and I've got the little detail on the right-hand side if you haven't had to use one in a while. But the total spread from maximum to minimum air tightness on the homes they tested. Then you've got the median and the quartiles, so the more common systems that were turning up in those testing, and the little dot is the actual average. So pre-1960s, we're looking at, call it 17 ACH, and that's air tightness at 50 pascals. Worth looking into air tightness versus air permeability. Homestar has made a call to move to air permeability, and actually referenced in their operational efficiency document, they're looking at permeability, which has a more surface area basis, not just volume basis. Coming down, you come closer to the 10s through the 60s and the 70s, and then all the way down to 5 ACH as we hit the 2010s. And a lot of the results we're actually seeing, and what brands are saying at the moment, is that they're expecting to see it be more around 3 ACH from 2020 onwards. So they haven't done a more recent study that they've published in a wonderful graph format like the previous one, but that is the testing and the information they understand from the current building codes. So what we've got here, we've just taken those averages out of that previous graph, and then we've used the N factor, and that's a value that essentially relates the air changes at 50 pascals to an effective natural air change. Now, there's a lot of variable conditions that affect that, but they've said it's around about 20. So that 20 applies right down to kind of 7 to 9 air changes. So what we've done is we've taken the average air change for our old home and applied a divide by 20. And that's resulted in the natural air changes we're getting now. Obviously, a lot of these homes still have moisture and condensation issues, but what we're saying is they're actually receiving the fresh air they require up until the late 90s. From 2000s onwards, though, not getting the natural air changes, and they're also becoming a lot more airtight. So what we're recommending here, and our recommendations are on the right, is that you look at any type of ventilation system, be it PIV, MEV, continuous mechanical extract, or even a heat recovery solution. So these are minimum recommendations. Anything before the 2000s is probably okay if they haven't renovated. On the other hand, after you've come through the 2000s, you need to start thinking about those recognized pathways for your air. Then we get onto the New Zealand climate, and this was quite interesting. Mentioned a little bit earlier that H1 came out and it made all of these changes that are affecting how we're building. But the other thing they did was they released the new climate map, which broke the previous 3 climates into 6 climates. Now, those 3 climates had originally been based off the NZS 4218 Thermal Insulation, Housing and Small Building Code, but the new ones, they haven't supplied a whole lot of guidance for them. They have in their consultation document identified where they compare each climate zone to, but they haven't really given us what that data is. So what we've done for this presentation is we've actually we had a look at both ASHRAE and NIWA, and we've put their temperatures into a spreadsheet. You don't need to read this, I've summarized it on the next slide, but we've put them all into a template and taken the minimum and maximums from those spaces. So that resulted in this little table here. So H1 as it relates to the ASHRAE data. We didn't use NIWA because of the age of that data. So ASHRAE was our preferred, but we did find in zones 4 through 6 that we could have potentially done with more locations. And that's just simply because the spread didn't end up very large. We took that climate data, taken those minimum and maximum temperatures, and then we looked at homes that were around 90 meters squared for the 22 litre a second column and 150 meters squared for the 36 litre a second column. And we said, how much energy are we going to need, or are we going to need any heating to get the incoming air in these climate zones up to 16 degrees? So that's the 16 degrees from G5 that we saw earlier. Now, interestingly, in a 22 litre a second, so a smaller home, 90 meters squared, you're looking at around and standard 2.45 stud, I think we ended up using. So we can supply all of those numbers to you if you need them. We found that you could actually use anywhere in the country an MVHR solution, but when you went from climate zone 3 to climate zone 4, you needed to make sure the efficiency of your core was higher. So that might be looking at cross-flow versus counterflow cores, where oh my goodness, too many C's. Cross-flow versus counterflow cores, where in the counterflow, there's a higher efficiency due to the air staying in contact for longer. If you're looking at a bigger house, though, that 60% dropped down to only working in climate zone 1, and you needed to go to 80% all the way through. You'll also see that in here we've said that you can get that temperature up to 16 degrees by using any ventilation solution with a heater. So what we've seen so far, we've had a look at the age and the climate, and you'd also want to define whether or not they actually need fresh air. And then we're going to want to think about, if you're comparing systems, the noise, the life expectancy, the maintenance. Now, that's something that you do need to get from your suppliers, so you can ask them for that data. But those would be the next components to cover. The last one, and that's the one I mentioned right at the start as being an interesting one, is actually the efficiency goals. So that's a little bit more challenging, and it does require modeling software. And what we've done is we've taken some data from our own systems and just done some comparisons. So you might have seen graphs like this before. Now, what we had a look at was a pure balanced solution with no heat recovery versus an MVHR solution. And we said the initial cost for the balanced solution was around $2,000, while for the MVHR, and this is theoretically installed, for the MVHR solution, you're sitting closer to $7,000. And what we looked at was we took the power usage of those systems, and then we said if they were running 21 hours in continuous mode and 3 hours in boost mode to deliver the requirements for those wet rooms. And we wanted to achieve 16 degrees without a heater for the MVHR, whereas as we said just before, we knew that balanced would require a heater no matter where it was in the country to get up to 16 degrees, although the data here is based on Auckland conditions. And the cost, the result is based on the 0.3734 per kilowatt hour. That's a lot of decimal points there, but bear with me. So what we found is after just under 7 years, you were paying back your MVHR solution. Those numbers do change if you're using a heat pump system or similar, but it's a really interesting comparison that delivers a lot more information for the homeowner, and making that kind of information accessible or for your clients, who the developers, the architects, making the information available to them is really important. And we need to work out a way to shift from that CapEx only approach that we see in a lot of buildings to a CapEx plus OpEx. And I think that energy efficiency standard is going to do it. So we took that information and we looked at it a little bit harder, and we went, okay, let's use the per meter squared capacity, the power capacity that we're going to require to heat that space per annum, and compare how well they perform. So again, we looked at it for every single climate zone, and we looked at what the electrical heating requirements, that's the first column in each of those sections, looked at the electrical heating capacity first and said, okay, you can get away with 30 kilowatt hours a year per meter squared in a smaller home, 90 meters squared, and it's about the same in 150. So that was great. Our numbers all added up, so we didn't need to start looking at both the small home and the large home. The meter squared rate was enough there. You could potentially argue maybe it needs to be volumetric, but we've gone with meters squared for now. And then when we looked through it, we said, okay, where do we use our MVHR system? Remembering that the electric heating, that's any vent plus a heater. We can have a look at an MVHR 60% and an MVHR 80%. And what we found, and we did feed this into the data earlier as well, was that in climate zones 1 through 3, a 60% efficient heat exchanger was going to do the job to get to 16 degrees, but in climate zones 4 to 6, you needed to go up to an 80%. And as we said, that part did change on a larger house, and that's a factor of the efficiency. Right, heating capacity. So we took it a little bit further, and I think actually, so that last slide was at 16 degrees. This next slide is at 20 degrees. And the reason I did that is we weren't seeing a whole lot of difference in that data. And 16 degrees isn't really comfort heating either. Like, it's not a comfortable temperature to live at. So when you change it to 20 degrees, the information does divide us up a little bit more. So you can see that MVHR at 80% is still a really low capacity required. Needs a little bit more to get it up to the 20 degrees, so we're not actually achieving 20 degrees with it, but it's not a whole lot of extra tempering. And you'll see with, say, passive house solutions that they require a heater on them, and some of that will be based on this. For the MVHR 60, you are now getting into the 10 kilowatt hours per meter squared per annum, and close up to 15 in the larger homes. So what does that mean? If you're trying to make a recommendation for someone, you can give them a high, medium, or low rating. Is that oversimplified? It's something we need to work on, but I think it's a really effective recommendation. So when you're looking at your solutions, you can get a 60% MVHR in that 16-degree target, but for the 20 degrees, you actually start to see that difference. So less than 10 kilowatt hours per meter squared per annum for your power to heat your fresh air. So that's your incoming fresh air if you are ventilating. You can use an 80% efficient MVHR, or if you only want to be on a medium solution, it's a 60% efficient MVHR system. If you don't really care, or you can use anything, a heater does work. And no issues with heaters or heat pumps. I think they are absolutely wonderful solution, but that is where they're sitting, is they are more on a low efficiency. You might find with a heat pump that you sit more in the 10 to 19 kilowatt hours per meter squared per annum, possibly even under 10. But that's an interesting way to look at it, in that you can actually start to evaluate whether or not it's delivering a target efficiency for your client. So just thinking about what we've gone through there, is it an oversimplification? I don't know if it is, because we know as engineers what we're dealing with here, but what we can't control is how many people are actually working through these things, how many people are doing these designs. So when we give them these recommendations, are we actually going to see the results that are going to deliver for New Zealand homes? Can we say things such as pre-2000s, any ventilation system is suitable, but after the 2000s, we really should be recommending prescribed air pathways? The climate zone, is 16 degrees the right target? That's what G5 gives us. And as I said, that's a commercial requirement. If we do say, yes, 16 degrees is the right target, then all zones require some kind of tempering, heater or heat pump or MVHR. And then you can use 60% to 80% MVHR depending on which climate zone you're sitting in. So that starts to actually get some clear advice for those places that further down the country. We know they're already starting to use more MVHR, but it starts to give solid numbers behind what we're recommending. Then we've got the efficiency levels. So as I said, I've taken that to 20 degrees because it gave a clearer differentiation between types of systems. And you have your high, medium, and low solutions, which you can put your kilowatt hours per metre squared per annum on there to relate it to. So I don't think it's an oversimplification when we think about the kind of audiences we might be dealing with. We need the consumers to understand what we're actually trying to tell them. We need our clients to understand what we're trying to tell them. And we don't want to be building homes that wind up with a condensation issues two years down the track. Now, I'm going to have a quick look deeper at building code. So this is a big discussion that's going on at the moment, and the industry is reasonably vocal, but maybe not in the right places. So what we've put up here is some suggestions on what we could look at for where building code needs to go. So one of the elements is splitting G4 into residential and commercial, and I'm going to relate that just quickly to what they've already done with H1 and G7. So for H1, we already see 3 verification methods. We've got 2 acceptable solutions and a verification method. And they are targeting different size buildings and residential versus commercial. They have divided it up that way. You can see the same thing in G7. It's got 3 again, and they have got, for the sub 300 metre squared buildings or non-complex buildings, a separate solution for residential. So I think that's what we need to go with G4, and we need to do it soon with what's already happened with H1. We want to look at extract versus fresh air, and that's a discussion around what the actual requirements are for extract. Are the current standards delivering what we need in a bathroom? Is 25 litres a second enough air to stop your bathroom from fogging up and creating moisture and having it stay there? Do we need to add a time factor? Do we need to move more air? Do we need to use automation and humidity sensing that's available in a lot of fans now? So these are all things that need to be addressed as we go through the building code. For fresh air, it's 0.35 a sufficient amount? Should we be at 0.5 like some recommend in Europe? I haven't got all of the answers to some of this, and that's actually the important part of what we want to discuss here as well, is that it's part of bringing all of this information together and giving clear advice on where it needs to go back to MB. We need to talk about whether or not an air tightness standard is required. That operational efficiency guide is looking at including the infiltration rate as a measure. So if we aren't advising people on how to design to the right standards, are we going to miss that part? And does it need to come under G4 anyway, or is it a separate situation? So air tightness for me is really critical to which solution you're choosing. It does work in older homes to use a system that is unbalanced. But when we're looking at those newer homes and looking at that data from brands, we're seeing that those changes have already happened, and that's before H1 went through. Possibly even more critical is the effect of the climate change program, and that's going to affect our minimum acceptable solutions and how efficient they actually are. So what performance they're delivering for the home. They're going to have a look at the need for actually commissioning those systems. So we can put in whatever we want, but if someone installs it with a U-bend or wraps around, I mean, how many examples have you seen? I've seen dozens where they've just taken the full length of ducting and left it lying in the ceiling. So the need for installation compliance and commissioning requirements for installers, is that something that's going to be beneficial, or is it just that we need to make sure there's more training and advice out there? And then the last one I've just got on there is designer competency and qualifications. For a mechanical engineer, ventilation is not always, it doesn't feel like a complex subject. I think that's what I'm trying to say. But for a lot of people, it's far harder and there's a lot more to it. And we've been through some of that today than just providing a fan with a certain airflow. You need to understand what the rest of the system is. You need to understand how well it's been installed, what your environment's like, how the users are going to use the space. That's another critical component, harder to control, in fact, almost impossible to control. And then that needs to feed into our decisions. So it's a really convoluted space to be in with what could have been quite a simple subject if you just looked at the building code. And that's a challenging place to be for New Zealand. So I bring it back to what's needed. We do need to collaborate. This is what we've put together. These are the recommendations based on the evidence we've been able to collect. We've put this through our selection software and we've modeled the performance of our heat exchangers to try and get that information and given it a clear way of recommending it based on different efficiency classes. Is that enough? Is that high enough definition? And then once we've made those definitions, how are we going to change and educate the market? And we really need feedback. We need to be working together and we need to be feeding back on that. So I've popped some contact details at the bottom of the slide, but I think, and I've tried to go a little bit fast because I really wanted to give time for questions and answers. I think the discussion part is almost more important than the content on its own. So I hope you've all learned something today, found that interesting. I can flick back to any of those slides if you'd like to see them again. And as I said, I will be sharing them after. So thank you very much. I'll let Jaren run the question and answer session.
Hey Storm, thanks for that presentation. It was really good. Really like the slide with the potential changes to the building code that you had up. Some thought-provoking points there, which obviously is essentially enabling better change, for the construction industry and just, the whole ventilation strategy in buildings across New Zealand. Before I get to the Q&A, I have put a poll up on the chat box. So far, I've only received 9 responses. We've got 19 people, and about 4 of them are from CIBSE, but so there's probably another 6 or 7 more responses that I would like. Just asking about your field of occupation in building services. I'm also going to put up another poll. This is essentially asking for your consent to share your name and contact details to CIBSE. So I'm just about to put that in now. And yeah, it's done. So it'd be great if you guys can fill out those 2 very quick and easy polls. Cool. Now, just to kick off the Q&A, feel free to add your Q&A. Add your questions into the Q&A box, or if you want to, I don't know if people are able to talk or if I have to unmute them.
We can unmute you.
Okay. All right. Cool.
What I'll do is I believe it'll send you a request when I click on it.
Yeah, I guess people can just raise their hand, or if they want to talk, or just type. Anyway, I'll start off with the questions. I had one for you, Storm. So for positively or balanced mechanically ventilated homes, is there a minimum indoor air quality with respect to air filtration or the outdoor air system?
Yeah.
With the, I guess, what you've talked about today.
Yeah, no, look, that's perfect. With the minimum indoor air quality with respect to the air filtration, there is the outdoor air standard in the building code, and there are some more details on that. There isn't beyond that particularly clear guidance on what needs to happen. I mean, at the moment we're dealing with naturally ventilated homes that opening a window is suitable. So the assumption is that outdoor air is sufficient high enough air quality. We see a lot
Okay.
more issues overseas in more populated
Mm.
cities, but no, not really at the moment beyond what I've seen from building code.
Okay. Cool. We've got one from Damien McGill. In your efficiency calculations, are you looking at the efficiency of the whole system or just the heat exchanger?
Yeah, great question, Damien. In that instance, we've just looked at the efficiency of the heat exchanger, so how much, whether or not it achieves 16 degrees or 20 degrees, and then what the temperature difference is and how much it would cost to bring that temperature up to the target temperature. We did discuss whether or not we wanted to look at the efficiency of the heat exchanger itself, and sorry, the unit itself, so the fans running. And when I looked into it, just with the time I had, having the duty points and the performance of the fan at different fan speeds to deliver that air made it a lot more challenging. So I couldn't just put in 50 watts for one fan and 20 watts for the other. I needed to understand what it was actually running at as well for the performance, so what your static pressure and the resistance of the system was that it was trying to deliver that air to.
Do you follow up on that, Damien, or are you all good? You're muted. I don't know if you can
Sorry,
unmute yourself.
that.
You're trying to talk.
So you should be able to unmute yourself now. I've given that permission. Do you want to pop your response in the chat and we can respond to it there?
Yeah. Cool. Does anybody have any more questions for Storm on this topic of home ventilation?
I think I saw some comments in the chat just when I was having a look through just now. So there was one there on building for climate change and where the building for climate change is going. It's just a comment regarding it is effectively heading towards passive house standard. And there was a great question in there on whether or not we'd looked at the passive house zones for our data, and no, we didn't. So for that, the different climate zone recommendations where we went with ASHRAE, I don't believe we looked at the passive house solutions for that, no, but it's definitely something that could be considered. We just need to be aware of the different sources and where that information is coming from. So no, good question there. Have you got the ones in the chat there, Jaren, or I can keep going through?
I think it's more of a statement from Damien here. He said ducting types, lengths, and distances have a big effect on ventilation efficiency. I think it's in response to your
yes
answer to the previous one.
Yeah, I've just unmuted myself. I got that to work. Still,
well done, thank you.
Obviously the heat exchanger is just one part of the system, and the whole ducting system itself, the rest of the system has a big effect on efficiency.
Yeah.
So that's obviously much harder to feed into your calculations, of course.
Yeah.
But I think people need to be aware of the efficiency of the whole system, not just the heat exchanger.
Yeah, look, I do agree. The installation side of the job is a lot more challenging, and the education on that is there, it's available, but it's not necessarily accessed by the right people. And I think as part of that, and I put it in my building code suggestions at the end, I think it needs to be discussed as whether or not it does need to be covered off. It is, I believe, commercially a specified system. So HVAC is a specified system when the councils are looking at it. So when they feel like you've hit enough complexity to need sign off, then they'll get someone who's qualified to sign off, but it's not anywhere near the requirements of fire or electrical at the moment. I'm not saying we need that, but at the same time, because you don't want to put up barriers to people putting ventilation systems in the first place, but it's a question we need to ask as we move forward and as we look to getting G4 reviewed. Does it need to cover off installation as well? And I think definitely at least a recommendation or guidance on how the install should be done needs to be publicly available, more publicly available.
Hey, Storm, can I just add something in here?
Yeah, go for it.
Hey, Damien, that's a really good statement you got there with the ducting. And it's kind of a bugbear at the moment because H1VM3 has kind of thrown out R0.6 flexible duct. And it's a minimum of R1 now. But the residential part of H1, being VM1 and VM2, don't even bring it into discussion. So you can still utilize R0.6 in a residential application. And you're right, those type of things of ducting and lengths of ducting especially do have a massive impact on efficiency. So definitely something to look at.
Very
Do we
good.
have any other thoughts on are the recommendations oversimplified? I'd love to hear from the group. We've obviously done a lot of research behind the scenes to create those recommendations and model what we were going for. But is that dangerously oversimplified, or is that sufficient to deliver a strong recommendation to industry? Chat's great. You don't have to say it out loud.
I think design a system is critical, but when you're using a balanced system, commissioning to ensure that it's balanced is just as critical. So
Yeah.
it's the whole system. Anyone can design anything, but it's got to be put into how it's been designed for it to work. So commissioning is definitely a key part of this whole equation.
Yeah. Cool. Oh, I thought there'd be a little bit more questions and answers. Are we all just quite happy with how that's looking, or because I'm basically where we're going from here is we are working with industry to try and deliver recommendations for building code changes with that backup information. And if you have information on buildings that you've seen, particularly in the last 2 to 5 years, that are still getting built and having issues where ventilation was what was missing, please share them with us. I believe CIBSE will be able to supply our email address afterwards if you haven't got it already. So me or Darren Gear would be great contacts there. But is that the right way to go? Are we hitting the right notes? Are we having the right suggestions there? Or is there something else we need to think about as well? I know there's some conversation, particularly in the building science space, around updates to E2 as well. So your weather tightness standard, not just your internal moisture standard, and how that affects the air tightness of our builds too. So really keen on that feedback. I think it's really, really important. And if you want to be involved in future as well, please get in touch. So do share your contact details with us so we can reach out, and if you're interested in being involved in that feedback. I think it's important to have the more voices in there.
Okay. All right. I guess once again, thank you, Storm, for that great presentation on home ventilation. And I think that'll will come to an end. Thanks for everyone who's joined in from around New Zealand. I presume there's nobody from Australia, I believe. Yep. Hope that was educational for you guys and useful for your profession, and hopefully see more of you in the upcoming CIBSE CPDs. So we have both webinars and in-person technical events that occur every year. Oh, sorry, at least once a month this year. All right. With that, have a good day. And
Excellent. Thanks all.
catch you
Thank
later.
you. Bye-bye.
Thanks
Cheers.
all.
Bye.
That was great. Bye.